Think of an algorithm like an engine. As you feed it a larger and larger data workload, which we represent as n, we need a reliable way to measure exactly how fast it burns through processing time. Look at these trace tables mapping out two different loops. On the left, a loop updating its counter by simple addition, like I++, steps through the data one by one. This requires O of n time. On the right, a loop updating by multiplication, like I times equals 2, leaps through the data, reaching n in a fraction of the steps. This costs O of log n time. This handwritten code snippet shows what happens when we stack these structures. Here, a linear O of n outer loop wraps around a logarithmic O of log n inner loop. For every single step of the outer loop, the inner loop executes its entire logarithmic sequence. Their costs multiply, giving us an overall time complexity of O of log n. A single character change in how a variable updates dictates exactly how an algorithm will scale in production. Here is a common trap directly from the foundations section of the exam paper. Do both 2 to the power of n plus 1 and 2 to the power of 2n belong to the exact same O of 2 to the power of n complexity class? To find the answer, we applied the strict mathematical requirement for big O. A function f of n is big O of g of n only if it is less than or equal to a constant c multiplied by g of n for all large values of n. Let's test 2 to the power of n plus 1. By exponent rules, we can pull out the 2, expanding this to 2 times 2 to the power of n. This matches our definition. We have a valid constant of 2 satisfying the rule, proving it is indeed O of 2 to the power of n. Now we test 2 to the power of 2n, which expands to 2 to the power of n squared. If we plug that into our big O equation, we need it to be less than or equal to c times 2 to the power of n. Divide both sides by 2 to the power of n, and the equation simplifies to 2 to the power of n is less than or equal to c. Because n grows to infinity, it is mathematically impossible for it to stay smaller than a fixed constant. It fails the test. Exponents that look nearly identical on the surface often belong to entirely different efficiency classes. Exact mathematical bounds prove how they actually scale. This page outlines the general formula for the master theorem. T of n equals a t of n over b plus f of n. This formula acts as a scale to weigh the work in divide-and-conquer algorithms. A represents the number of subproblems, b is the division factor shrinking the data, and f of n is the cost to divide and combine the work at the root. The theorem balances the work done at the deepest leaves of the recursion against the work done at the root. In case 1, if the leaves, calculated as n to the log base a of a, are polynomially heavier than the root f of n, the leaves dominate the overall complexity. Case 2 is a tie. If both sides weigh the same, every level of the recursive tree costs an equal amount. To find the total complexity, we multiply the weight by log n. In case 3, if the root work f of n is polynomially heavier, and it passes a specific regularity condition, the root dictates the final complexity. Let's apply this scale to a real exam problem. We need to solve the recurrence t of n equals 2t of n over 2 plus n squared log n. First, we extract our variables. We have a equals 2 and b equals 2. Plugging those into our leaf formula gives us n1. We compare this leaf weight of n to our root work, n squared log n. The root is polynomially larger, meaning case 3 applies, and our final complexity is theta of n squared log n. Try this one yourself. T of n equals 8t of n over 2 plus theta of n squared. Pause here and determine which side of the scale weighs more. Here is the breakdown. With a equals 8 and b equals 2, the leaves calculate to n cubed. The root sits at n squared. The leaves outweigh the root. This falls into case 1, resulting in a total complexity of theta of n cubed. Treating recursive complexity as a comparison of mathematical weights allows the master theorem to completely bypass the need to manually trace every level of a function. This hand-drawn recursion tree maps out the problem t of n equals 4t of n over 2 plus n to show how work accumulates. Look at the per-level sums on the right. The root costs n. The next level splits into 4 parts, costing 2n. The level below costs 4n. The cost doubles at every step, forming a geometric series. N multiplied by 1 plus 2 plus 4 down to 2 to the k, where k is the tree's depth. Since depth k is log base 2n, substituting this yields a dominant term of 2n squared.
leaving a complexity of O(n squared). The recursion tree provides the visual proof that justifies the strict mathematical boundaries of the master theorem. This cheat sheet consolidates our findings into an actionable reference guide for algorithmic analysis. For iterative code, recall the basic structures. I++ yields linear time, I times 2 yields logarithmic time, and nesting loops multiplies their total cost. For recursive code, the master theorem calculates the winner in a strict mathematical weigh-in between the problem's leaves and its root. Mastering these specific mathematical tools allows you to rapidly predict how any algorithm will behave as its data scales.